Continuing on Physical Chemistry, Chapter 3, we're beginning Section 7 now. So what is entropy? Well, the zeroth law says that temperature is proportional to the average kinetic energy. So let's say we have the temperature of three objects, like before. If A is in equilibrium with B, and C is in equilibrium with B, then A is in equilibrium with C. We mentioned that before. Now, the first law says that internal energy is proportional to the total molecular energy. Which brings up the obvious question, the second law, entropy is proportional to what? Now, let's look at a molecular interpretation of entropy. Now, let's say that we have two inert gases. One is called E and one is called D. This is completely arbitrary. They can be helium, argon, it doesn't matter. So our initial state is with them separate. We have E on one side of the system, D is on another side of the system, and we have a partition between them. Now we're going to remove the partition. Now immediately, this is a transition state. Nothing's going to happen just yet. We still have the E over here, we still have the D over here, because they haven't had time to do anything. Now, as we approach equilibrium, we're going to start moving stuff around. We'll have the E's and D's on both sides, and we'll have the D's and E's on the other side. We'll have E's and D's everywhere. Notice that this intermediate state is less probable. If we were to just say, oh, look, this is how it separated itself, you'd probably say, well, that's very improbable. On the other hand, when you have it completely mixed, there's so many different ways to do this, we would say that this is a much more probable state than this one, or the original. This is our equilibrium state, the D and E both mixed together. So the approach to equilibrium is spontaneous, from less probable to more probable, and it is irreversible. Now let's start with one box that has helium atoms. We're going to use lowercase p for probability, or more specifically, the probability that all the helium atoms are on the same half of the container. Now, if the container has only one part to it, and there's only one helium, the probability is 1, because, well, 1 basically means 100%. 0, remember, probability goes from 0 to 1. Now, let's say we have the same container, just one helium, but we have the container in two halves, like I said before. Well, the probability that the helium atom is going to be over here is 1/2, 1 over 2. Now, let's say same thing, we have a container, there's two parts. But now we have two helium atoms. What's the probability that both helium atoms are over here on the same side? Well, it's 1/2 squared. Likewise, let's say we have a container and with three helium atoms. What's the probability that all three helium atoms are on the same part? Well, then we would say it's 1/2 to the third power. Likewise, let's say we have a whole mole of gas, Avogadro's number. Remember, capital N is the number of molecules, lowercase a means it's Avogadro's number. So let's say that we have a container, and we want to know what's the probability that all the helium atoms happen to be on the same side of the container. The probability would be 1/2 to Avogadro's number. That's not technically equal to 0, but it's so close to 0 that we're going to just round and say, yeah, it's 0. So that's why, a couple things. One, increasing the volume, it actually increases the entropy. This is always true. Now, it may not be obvious here because of where we divided it into two pieces, but you think about it, bigger and bigger volume, that's actually more and more pieces. So let's just postulate for now that entropy is a function of probability. Remember, this is lowercase p for probability, not to be confused with capital P for pressure. So lowercase p is probability, capital P is pressure. So what is this function? Well, like I said, we got this container, and we're going to just say for now that it has two parts. And they're separated by a rigid adiabatic impermeable wall, which basically means these two parts right now are isolated. So the entropy of parts 1 and 2 is the total entropy of our system. So it's extensive, so it'll be the entropy of part 1 plus the entropy of part 2. Now let's say that we have a function h. So h is the probability of 1 plus 2 happening. And that's the function of probability 1 plus, or f of probability 1 plus g of probability 2. So we got these arbitrary functions just so we can keep everything straight. So remember, when you have independent events, and we talk about the probability of them both happening at the same time, you multiply the probabilities. So the probability of event 1 and the probability of event 2 is the probability of event 1 times the probability of event 2. So likewise, if we have this function h of probability of part 1 and part 2 is going to be equal to the function probability 1 or part 1 plus g of p2. But h of xy is going to be equal to f of x plus g of y. So logarithms, remember, these are functions that we can use to convert addition and multiplication, like we're doing up here with the probabilities. So we could say that the log, base 10 in this case, of a times b is equal to the log of a plus the log of b. Or we can use natural log. We're actually going to say, okay, entropy is some constant k times the natural log of probability plus a. So a and k are some sort of constants. We don't know what they are yet, but we got to try to see if we can derive them or something. Now a can't be determined, which is why thermodynamics can find the change in entropy, but not absolute entropy. Now remember, that's emphasis on the thermodynamics though. So if we have h of x times y is equal to k times the natural log of x times y plus c. And f of x is equal to k times the natural log of x plus a. This is a different a from up there though. We're kind of recycling letters here. We ran out of fresh letters, I guess. And then g of y is equal to k times the natural log of y plus b. And then we're going to just define another constant, c is equal to a plus b. Now this is just a totally new and arbitrary constant for now. It's not the speed of light or anything like that. So a, b, and c, these are just constants we need to figure out. Same with k. This is the same for all three functions though. So what we need to do is find a value for k. So the first, we're going to take this system in an unmixed state, just like we did originally. We have all the d's on one side, all the e's on the other, and it's got some sort of temperature, pressure, volume, entropy at state 1. This is lowercase p. So we have pressure and a probability of state 1 here. This state 1 means, the probability of state 1. Now we have our mixed state. We have all the d's and e's somewhat randomly mixed in together, and it's going to have another temperature, pressure, volume, entropy 2, and probability 2. So notice we're keeping the same temperature, pressure, and volume. It's just the entropy that's going to change and the probability that's going to change. Hopefully we can find a relation between the two. So obviously the change in entropy is going to be entropy 2 minus entropy 1, since it's a state function. So that's going to give us k times the natural log of probability of state 2 plus a minus k times the natural log of the probability of state 1 plus a. Of course, the a's are the same, they'll cancel out, so it doesn't matter what a is. We will have no way of knowing anyway. So we get the change in entropy is just going to be k times the natural log of p2 over p1. So the probability of state 2 divided by the probability of state 1. Now we're going to say, okay, remember capital N is the number of molecules. So the probability of state 1, which is with the stuff separated on each side, assuming 2 halves, is going to be 1/2 to the number of molecules of D times 1/2 to the number of molecules of E. Remember, when you multiply, you add the exponents, assuming the same base, of course. So we have 1/2 to the power of the number of moles of A, or the number, molecules actually, the number of molecules of A, plus, capital N is the number of molecules, lowercase n is the number of moles. I should have made that clear earlier. Plus the number of molecules of E. Now the probability, because they're all mixed together, it's almost certain, we're going to say is roughly equal to 1. So to simplify, we're just going to say, okay, the number of D molecules is equal to the number of E molecules. So we're going to substitute in ND for NE and just go with that. So delta S, the change in entropy, is equal to that constant K that we haven't determined yet, times the natural log of 1 over 1/2 to the 2 times the number of moles of D. So taking that, we're going to take this K times the natural log of 2 to the power of 2 times the number of molecules of D. And that's going to be equal to, taking this 2 down in front, 2 times the number of molecules of D times K. Remember, you can pull exponents out of the natural log. So 2 times the number of molecules of D times this constant K times the natural log of 2. So this is going to be our equation 1 to refer to later on. So the change in entropy is going to be 2 times the number of molecules of D, substance D, times this constant K times the natural log of 2. So delta S, the change in entropy, is going to be minus R times all this quantity, the number of moles of A times the natural log of the mole fraction of A, plus the number of moles of B times the natural log of the mole fraction of B. This was from chapter 3, section 4. If you don't remember why, you might want to go back and review. Since we assumed that the number of molecules of A is equal to the number of molecules of B, actually we did E and D, now we're back to A and B, but that shouldn't confuse you, just follow along. Then the mole fraction of A is equal to the mole fraction of B, which is equal to 1/2. Now remember, the mole fraction of A can also be written as the number of moles of A divided by the number of moles of A plus the number of moles of B, but we said they're going to be the same just to keep the math simple. So we're going to have the number of moles of A divided by 2 times the number of moles of A. These cancel out and end up with just 1/2 for the mole fraction. So the change in entropy is equal to minus R times this quantity of 2 times the number of moles of A times the natural log of 1/2, which is equal to 2 times R times the number of moles of A times the natural log of 2. So now we have equation 2, that delta S is equal to 2 times R times the number of moles of A times the natural log of 2. So now these are both equal to delta S, so we're just going to set equation 1 equal to equation 2. So we have 2 times the number of molecules of substance D times K times the natural log of 2. We actually missed A and D here. We should have been more careful here. We'll call this one D. You get the idea. But anyway, so times K times the natural log of 2 is equal to 2 times R times the number of molecules of D times the natural log of 2. The natural logs of 2 cancel out, the 2's cancel out. We just get the number of moles of D times K is equal to R times the number of moles of D. So we just solve for K. K is equal to R times the number of molecules of D divided by the total number moles of D divided by molecules of D. So remember, when you're dividing molecules by moles, that's just Avogadro's number. So actually what we end up is K is equal to R divided by Avogadro's number. Now remember what we said before, Na is equal to Nd over Nd. Oops. Oh, that should have... Oh, Avogadro's number. Yeah, capital A. So Avogadro's number is equal to the number of molecules divided by the number of moles. Now remember, R and Avogadro's number are fundamental constants. I mean, you see this all over the place. You see this all over the place. So a ratio of these two, that also makes K a fundamental constant. This is very important. So K is equal to R divided by Avogadro's number. We have, for R, a value of 8.314 joules per mole per Kelvin. And then for Avogadro's number, this is kind of strange wording, but you have 6.02 times 10 to the 23 molecules per mole. Your book explains this is silly because molecules isn't really a unit. But if you write in molecules, it makes more sense. If you leave out the molecules, people wonder what we're looking at here. But notice the moles cancel out. Therefore, K is equal to 1.38 times 10 to the negative 23rd joules per molecule per Kelvin. Which again, molecule isn't even really a unit, but if we just said joules per Kelvin, you'd probably think it was heat capacity or something. So K is equal to 1.38 times 10 to the minus 23rd joules per atom per Kelvin. Now also notice, K is called Boltzmann's constant. if you've taken chemistry or maybe physics before, you might have already heard of Boltzmann's constant, because K is a fundamental constant of the universe. So entropy is equal to K times the natural log of W. W is the number of microstates. W is proportional to probability. And remember, obviously W is not work in this context. Now K plays the same role as R in equations, but with R you're talking about bulk matter. You're dealing with moles and so on. K is what you use when you're talking about one atom at a time. Now let's further look into microstates and probability. Let's say we have two fair perfect coins. Then if you flip them and see what you end up with, you could either end up with heads heads, tails tails, heads tails, or tails heads. Now this is actually 4 different microstates because order matters. Except you'll notice heads tails and tails heads, these are really the same. It's one head and one tail. So we actually say there's 4 microstates but 3 configurations. Now let's talk about energy levels of a system. Let's say your system can have 2 different energy levels here, energy 2 and energy 1, but you have 3 molecules. Well, then you could have all 3 molecules in at energy 1. You could have 2 of them at energy 1 and 1 of them at energy 2. You could have 1 of them at energy 1 and 2 of them at energy 2. Or you could have all 3 of them at energy 2. Now this, because these atoms are all the same, we're going to say, oh, that's weird. I'm actually going to look into this. I'm not sure if this is right. But according to this, there's 4 microstates here. All 3, 2, 1, 0. It says here there are 3 configurations. I'm not sure why. I'm going to have to look into that again. Okay, so let's say we have N2 over N1 is equal to E to the minus delta E over KT. So delta E is the change in energy, K is Boltzmann's constant, T is absolute temperature, E of course is the natural number. So the delta E, that's the energy difference between these 2 states. So it would be E2 minus E1. Now this doesn't apply with degeneracy. We haven't even talked about degeneracy yet, but we will. So keep that in mind. Now for electronic states, the distance between here is roughly 10 to the minus 17 or 10 to the minus 18 joules. But let's say that we are pretty high temperature, like 5,000 kelvins. Well then let's put the numbers in and see what we end up with. The N2 over N1 is equal to E to the minus 1 times 10 to the negative 18 joules. So we went with this number here. Divided by 1.38 times 10 to the negative 23rd joules per Kelvin. Notice we didn't put in molecules or atom or anything like that for the unit because it's not a real unit. Times 5,000 kelvins. All these units had better cancel out because they're in the exponent. You're not going to want any units in the exponent. So that just gives us E to the minus 14.49 power, or 5.1 times 10 to the negative 7. So if we have 10 million molecules, we should expect just 5 of them to be in the energy 2 state. The other 9 million will be in the energy 1 state. So like I said, out of 10 million atoms, just 5 are at E2. So what about if we increase the temperature to 10,000 Kelvin? Well, then we're going to end up with N2 over N1. We're going to end up with 7,000 over 10 million. So if we have 10 million atoms, 7,000 of them will be at energy state 2. Now this is assuming that we only have 2 energy levels and no degeneracy. Now that's why that we ignore energy, electronic energy, when we're calculating the heat capacity, the molar heat capacity at constant volume, because it's hardly any of the atoms or molecules are going to be in the higher energy state, so it won't make hardly any difference. And like I said before, within electronic energy levels there are vibrational energy levels, and then within vibrational energies there are rotational energy levels, and then within rotational energy levels there are translational energy levels. And translational energy levels are so close together they're practically a continuum. Now let's talk about methane, Ch4. So the molar heat capacity at constant volume comes from translation, rotation, and vibration. Now we're going to say the temperature is roughly 2800 Kelvin. Now remember, the translation has 3 degrees of freedom, so that's 3/2 R. And then for rotation, because of the type of molecule, we have 3/2 R. And then for all the different vibrational modes, we have 9 R. So the molar heat capacity for methane is going to be 13 R. And remember, heat capacity, the molar heat capacity at constant pressure is equal to the molar heat capacity at constant volume plus R. Now let's talk about spectroscopy, actually looking at these. So electronic levels, because of their distance apart, you'll see that in the visible spectrum or the ultraviolet spectrum. Now vibrational energy levels, because their energy levels are closer together, you'll see that with infrared spectroscopy. And then if you're the microwave energy levels are even closer together. So with microwaves, you'll see the rotational energy. And then translational is so close together, we don't have the technology capable of actually seeing that. You can't do spectroscopy on a translational energy, yet at least. Entropy is technically a measure of disorder, kind of like in general chemistry. Since disorder, it's not technically a measure of disorder, because disorder is subjective. Probability is a precise mathematical concept. So that's why we say that entropy is kind of related to probability. Okay, that is the end of section 7, and that is the end of chapter 3.